Hello guys, welcome back to the 31st August problem, and this is a linear algebra mixed probability problem, guys. So what's in this problem? Let's check that. So if you check the problem, it's asking that um, the three cross three matrices having three entries equal to one and six entries equal to zero. Okay, so that means actually that out of the nine matrix, there are three places which are one, and the rest of the six places which are zero. And the matrix, a matrix uniformly selected at random, and then which of the following are correct. Uh, Now, if you try to understand this, that the first step should be always counting the number of such matrices because a matrix is uniformly picked from that random set. So if we know the like elements of the number of elements of the set, we can understand this. We can actually, since it's equally likely, we can know that what is the probability of individual matrix. So we can add up therefore the numbers. Okay, so before that, if you have not solved this problem, please do like stop the video, pause the video, and do it yourself, and then come back to the solution. Anyways, let's go back to the solution right away. So there, it's a set of all the matrices, such that it contains like three places are one, and the rest of the six places are zero. So how many such matrices are there? It's very simple. So there are nine places, and out of that, we have to choose three places for the one, and automatically it will fix the number of the rest of the places of zero. So total number of such matrices is 9 choose 3, which is equal to around 9 into 7 into 6. 9 into 8 into 6. 8 into 7, sorry. Yeah. This number of matrices are there because we are choosing the three places for 1, and automatically it fixes the number of places for 0. So that is the number of elements in the S. So it's asking therefore various other conditions, that what is the probability that m is equal to non-singular, that is m is invertible, that is m determinant is non-zero. So one important idea we're using, that like to this, so it can be done by hand. Okay, we can jot down many of these things and we can do it, but that's not the way we are aiming to do it. We are trying to do it with a puzzle idea, like we are trying to do it with minimum effort and minimum logic, like the crispiest logic of all. So let's understand this. So we have this 8 in 9 700, like around I think 504 matrices. Yeah, I think, yeah, I did the calculation. 504 matrices. Out of that, how many are like non-invert, like invertible? Okay, how many have determinant zero? So how do you find that? So you have a matrix over here. You have three ones and six zeros. So you want to find it invert. You want to make it invertible. If you want to make it invertible, guys, what are the ways of doing it? Okay, what are the ways of doing it? And let's understand that very carefully. What are the ways of doing it? So the three ones. So understand that if you have a zero, so it means that zeros are there more in numbers in the matrix. If one row or one column has zero, 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 then that matrix is not invertible, right? That matrix is determinant zero. If one row or one column has zero, 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 then that matrix is. So the idea is that if one row or one column has 000 is 000 in fact, then the matrix is singular, that is determinant 0. Now understand that we are therefore trying to find out the number of ways there is always a 1 in each column and row. That's the idea. There's always a 1 in each column and row. If it is not there, then that means that column has 000 or row has 000. That means that is not invertible. So the number of ways, there is always a 1 in each column and row. So let's see. So there are three ones. Okay, there are only three ones. And to make that three ones, let's say there is one, like let's give one somewhere here, let's say randomly. And therefore, you have to make compromise all the other three rows, other two rows, and other columns. So it's like, in some sense, it's like Sudoku in some sense, not exactly, but So this for this one, this row and this column is done. So we have to use the minimum, like we have the minimum resources. We have to spread the maximize the effect. So one row and one column has been done. So let's look for the other row and the other column. So there are three other rows and three other columns. So let's skip it. So we have to make it in such a way that so the three other two rows and other two columns are done. So let's skip it one here, and similarly let's skip one here. So in this way only we can actually, using three ones, we can make sure there's always a one in each row and each column, and that's the only condition, right? That's the only condition. So how many ways we can do that? That's the idea. How many ways we can do that? Very simple. How many ways we can do that? Yeah, it's very simple. So what we do is the following. We have this matrix and we have this cross, 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 and this. So if you're trying to fill it up, what you get? You get that, what do you get over here? Understand it very carefully. Get that you're putting this six, like three ones over here. So out of this three places, you have three choices. So three. So once this one of the choices is made, you have other two choices left for the next two. So it's into two. And once you made one of the choices, there's only one more choice left in the last row or column. So that is into one. So six such choices. So there are exactly six such matrices which are non-singular. Which are non-singular. Okay, there are six such matrices which are non-singular. So we have done the non-singular numbers of matrices. So it's six by total number of each equally likely. So total number of six by 9 to 7 into 8. So it will turn out to be 9 by, I think, 40, 12. Yes. And I think it's 112 like this. I hope I have done it correctly. Yeah, so it's 1 by this, so which is not the case over here. M is non-singular is coming out to be 6 by like 6 by 72. Not sorry, 1 by 72, and here it's 6 by 72. So I think I have done it correctly. I'm most probably sure of it because I often do calculation mistakes. So I think I have done it correctly, and yep, that's it. So there are six such choices, and yep. So if you have any other method of doing it, please let us know. Okay, and let's see. Let's see the rank one case. Rank one is also really interesting. Rank one is really interesting. It's another type of puzzle. So it's all about to do one where one sits. So if you see one where one sits, so let's say one sits randomly here. Okay. So let's say there's a zero over here anywhere. That means since it's a rank one, this multiplies by zero will be only zero. So whatever here is, it is always this wall will be always be zero. So three zeros are done. Okay. There's another three zeros to be like put. So now understand that if you place one over here, one of the like matrices will be this, and let's say you put another one over here. So what you get is that it's one times one. So let's say that there's only another one left. So another one was here or here. Let's say one is here. Then that was also multiplied by one to give it here, right? So instead of this looking into zero, what if we look? So that is not possible because it implies four. Because if we are looking into rank one case, let's say one is over here, and let's see where the other two ones are. If the other two ones are like in different rows and different columns, you have seen it's non-singular. It's not possible. Uh, that means one of them must be in same row and one column. So in this case, it is like this. But understand, in this case, it is also of rank. Uh, yes, or it's also of rank two. We want rank one. So we want something like we want to fix a column. We want to fix the basic column, which will be a multiple of like the other one will be a multiple of that. Okay, the other like columns will be multiple of that. So understand that in that it must be looking like this. It must be all one, or it must be looking like this, all zero. Okay, because yeah, that's if other matrices are multiple of this matrix, that is what I'm telling. So therefore, this is very interesting. So how do you do it logically? So let's understand this. So let's fix one. Let's fix the one over here. So the other two ones, let's fix the other two. Let's see where the other two ones can be placed. The other two ones can be placed over here, and in that case, all will be 0, 0, 0. That is done. The other two ones can be placed. So that if fixing this, other two ones can be placed over one here in this case, and the other in other place. So remember that everything is a multiple of this. Everything is a multiple of this. Okay. So every other row is a multiple of this. So other one must be placed somewhere. Okay. So mainly it's 0, 0, 0 always. So therefore, understand it very carefully that if you place one over here, it is not possible. Okay, because it will be 0, so it must be 0. Okay, it must be 0. So let's see what is there here. If it's 0, then all of them must be 0. All the other places must be 0. And if there is 1 not in this place, it's not possible because here it will be 0. So if it's 0, if the elements over here are 0, okay, according to this, if the elements over here if you place 1 over here and the elements in the other places are 0, 0, that means all of the rest ones will be 0, 0. Understand this very carefully. Let's understand from the scratch again. Let's fix 1 over here. Let's see what is this. If it's 0, 0, then all of them must be 0, 0 because of the rank 1 property. Okay, if this is 0, 0, if you face this 0, 0, then all of them must be 0, 0, 0. Let's see if you don't make it 0, 0. If you make it 1, what happens? Let's not fix 1. Let's fix 0. So it can be 1, 0, 0, 1, but it's permutation of the same. So let's not look into that. So in this case, it will be like this. So it will be 1, 1, 1 again. So that's one case. We are doing 0, 0 case. Right. So now let's say 1 over here, because these are the following cases we can happen. 1, 0, 1. 1, 1, 0, 1, 0, 1. Okay, that's the other cases, and 1, 1, 1 are the another 1, 1, 1 is another case. Where others are all 0. So both of them are like rank 1 matrix. Let's look into this aspect, this case. So if you put 1 over here, there is 0, 0 over here. Okay, there are 4 cases: 0, 0, 1, 0, 0, 1, and 1, 1. Now, if there is 0, 0, since it's rank 1, all of them must be 0 because it's multiplied by 0 only. It's become rank was like 0. So all of the other, whatever is there, it must be 0, 0. So all of them must be 0, 0. Here, similarly, 1, 1, 1 is here. So all of them, the rest 6 zeros are left. So this must be 0, 0 all. So let's keep these two cases. And if you solve one of the cases, the other case is automatically done because it's like symmetric in these two columns. So it's 1, 1. So if it's 1, 1, whatever x is here, it must be x. And y is there, it must be y. So x cannot be 1 because if it's 1, another 1 must be there. There's only exactly 1, 1. So therefore, this must always be 0. So if it's 1, it must also be 1 because it's a rank 1 matrix. So therefore, it must be 0, it must be 0, it must be 0, it must be 0. Now, understand very carefully. Now, let's check this any of them 1. If you take any of them 1 and the other one to be 0, automatically turns out it's a rank 2 matrix. So you can also find out the number of rank 2 matrix, rank 1 matrix. So we have found rank 0 matrix. We have found out the rank. We are finding out the rank 1 matrix. We have found out the rank 3 matrix. Now we are finding out rank 1 matrix. We are finding out now. You can after the homework you can find out rank 2 matrices. So therefore, it's turning out to be rank 2 matrix. Similarly, it will turn out to be rank 2 matrix. So there are 2 such rank 1 matrix are there. That's 1, 1, 1 must be always together. Okay. If 1 is over here. If so, the here cannot be no 1. Similarly, here cannot be no 1. Like since 1 and 1, it's the same idea. Okay, so there are 2 rank 1 matrix. Since there are 2 rank 1 matrix, it's 2 by 9 into 8 into 7. I hope I've done it correctly. If I have done it wrong, do let me know in the comments, okay? Or if you have any other idea, do let me know in the comments. So we have found the number of rank 1 matrices now. Now let's see uh, what is the probability that aim is equal to identity. Now if aim is equal to identity is the only one choice, like this. 1 1 1 0 0 0 0 0 0. So only one choice. Okay, and it is involved in the rank 3 matrices. So it's 1 by 9 to 8 into 6 into 7. So that's not the case. So let's see whether trace of 0 is equal to what? What is that? Trace of 0. Trace of m equal to 0. So trace of m equal to 0 is very interesting. It's like there is the matrix made up of 0 and 1. If trace of m is equal to 0 only if all of them are 0. So you have to like arrange the rest of the ones and the zeros in this place. So out of the rest of the 6 place, you choose 3 places for 1. Automatically it fixes the rest of the places for the rest of the places for the zeros, right? uh yes, it automatically chooses the rest of the places for zeros. So 6 choose 3 by 9 choose 3 total number of cases. So 6 into 5 into 4 by 9 into 8 into 7. Am I doing it anything wrong? Let's check. I think I am. Yes, so trace is equal to 0. So 6 12 over here, 3 over here. So yeah, it's 5 by 21. It's coming out. So none of the options are matching. So I must have done wrong somewhere. Let's check what I have done wrong. So trace of m is equal to 0. So all of the diagonal entries will be 0. So 6 choose 3 by 9 choose 3. M is equal to identity is 1 by 14. No. M is non-singular. Let's check that. Let's revise that. So M is non-singular. How we have done it? We have done it by the method of that. Have I missed any other cases? I may have missed some cases over here. Let me check. So this is the way I have explained in the problem that there are, so each row and each column, so permutation matrices, I think I've done something wrong over here. Let me just check. 6 places we have seen. 3 into so 3 places for 1, then the rest of the 2 places for yes. So if that is not the case, I don't know why my answers are not matching. 1 1 1 3 cases for this. So the rest of the 2 places 2, and it automatically fixed. I don't think there is other non-singular matrices over here. Rank 1 case check karte. Oh yes, I have done some mistake. This mistake I have done it. I don't know whether, I mean, yeah. The mistake is that I have fixed 1 over here, but there can be other cases also. Okay. The rank 1 case. So let's check that. Let's count that. So in rank 1, what we have done, like you have fixed 1 over here, and we have seen how many such matrices are there for that piece of 1. So we have seen that the only other thing, we have seen that 1 1 over here, 1 1 over here. It must be looking like this. So this 1 can happen here in the middle and here also. and this one can happen here and here also. So there are 9 such cases that are happening. So it's coming out to be 1 by 56. Okay, I have done another mistake. Yes, here the mistake I have done is the following, that I have counted 9 choose 3 wrong. It's 9 into 7 into 6 by, I think, 6 factorial. Yes, sorry, 3 factorial, which is 6. So there is another 6 over here which I have missed, and so it's coming out to be 1 by 14. Yes. Yeah, so I have done that wrong mistake by cross mistake. So yeah, so this is this, and into 6 over here. Oops, something is going wrong. No, here the 6 is automatically cancelled by Cheenta proper. That's not an issue. 5 by 21 is the answer over here. Perfect. So in this case, I have missed something, some other cases. So in rank 1, there are all these ones must be together. That's what we have understood. So 1, 1, 1. In the column, we have 3 options, and for the row, we have 3 options. So 6 by this. So it's 6 into 6 by, again, 9 into 8 into 7. I think I am doing it correctly. Yeah, 6 options for this, and similarly here also 6 options. So I think both of them is 1 by 14. It's coming out to both of them is 1 by 14. It's coming out. Why 6? Because the one singular matrix are the following. The rank 1 matrix singular are the following, where 1, 1, 1 are here, 0, 0, 0 are here, 0, 0, 0 are here, and there's another case like this, 0, 0, 0, 0, 0, 1, 1, 1, and the other cases are 1, 1, 1, 0, 0, 0, 0, 0, 0, and similarly other 3 cases. So 6 total of here. And similarly, the identity matrix, you can understand they're all the permutation matrices if you know permutation matrices. So we have got both of them to be 1 by 14. So 6 by 9 into 7 into 6 by 9 into 7 into 8 into 6, 9 into 8 into 7 into by 6. So we get, I think, 36 by 72 into 7, which is turning out to be 1 by 14. So yeah, it's a really beautiful problem. So for this, we have got, so actually total number of matrices are not that, but it's total number of matrices are, I think, 6. So it's 12 over here. So it's 84. So 84 such matrices are there over here. And out of that, number of non-singular, which coming out to be, non-singular coming out to be 36, sorry, 6. Rank 1 is coming out to be 6. Okay. Rank 0 and rank 2, it remains your homework. Okay. So rank 0 is whether it can happen or not. Rank 0 means all of them are 0. So that's not possible. So there's 0 over rank 2. Therefore, you can find out rank 2 is rest of them. Okay. And whether they are rest of them, or if I have done some calculation mistake, just let me know in the comments. Okay, I can do some calculation mistakes, but I think it will be in the same like order of thinking, and also you can have your own order of thinking. So please let me know like your thought process and how you did it. Okay, so it was a really nice problem. It's a really beautiful problem, and yeah, I enjoy doing it alive. So yeah, all the best, and if you enjoyed it, do like, share, and subscribe to your friends and those people who know. And regarding the ISI, sorry, IIT Jam MS 2022, we have our short 3-month crash courses for you guys. So if you want more information about that, do check the comment box. Sorry, not comment box, the description box. And yep. So all the best, guys. Stay tuned and stay blessed. See you in the next video. Bye.